Hello. Thank you for joining today's DataCon LA session, where we introduce a technical solution for turning trending search interests into product recommendations. I'm Mike Limcaco, an analytics specialist with Google Cloud's customer engineering team. Over this brief session, I'll describe how we can take Google unique data in the form of search trends and use readily available cloud computing services to then service the most impactful content from your own product catalog. We'll then leverage some demonstration datasets and highlight where this solution fits best, given an overall product recommendation strategy. All right, so let's dive right in. First, let's set some context. I think it's safe to say that many of us have our mix of favorite digital experiences, with apps providing social media, gaming, news, and lifestyle content to consumer-friendly streaming media services, delivering on-demand access to popular music, podcasts, and online video content, for example. Many of these applications drive engagement through a continuous stream of recommendations which reflect, or at least attempt to reflect, what users may find interesting or compelling in the moment. In the case of building a dynamic user interface focused on driving user engagement, then, how can we tap into what's hot, what's trending, and use these broad customer signals to create what we would call the top shelf on the front page of an end user application? We'll zero in on this challenge for today's discussion. That is, how can we design an application landing page with a number of rails or shelves that promote content which reflects what people are actively exploring, discussing, comparing, buying, promoting, and sharing across their respective communities of interest. To do so, we have to address three key technical challenges. Number one, how do we aggregate trending internet search interest at scale? Number two, how can we then turn these interests into targeted discovery operations against our content catalog? And finally, number three, how can we then further refine these candidate results into thematically or semantically relevant recommendations? We'll spend the next few minutes introducing three key Google Cloud Platform services that we can use to build an integrated solution for addressing these three challenges: data signals, retail search, and Vertex AI matching engine. First, data signals. Data signals is a unique data set that provides aggregated understanding of what's trending across the Google search service, broken down by search terms spread across geographic focus areas. For over a decade, the Google Trends web service itself has provided a sample of overall Google search data. This data is continuously processed in a safe and secure manner. Search trends data is anonymized, indexed, normalized, aggregated, and now published as a public data set available through the BigQuery Cloud Data Warehouse platform. This BigQuery dataset, known as data signals, allows users to measure interest in a particular topic or search term across Google Search, from around the United States down to the city level. Whether you're a marketeer, an executive, or an ops manager, you can easily ask what people are searching for to inform your analysis. Say you're a merchandiser in retailing and want to ensure your end cap displays are relevant to your local audience. You can take signals from what people are looking for in your market area to inform what items to place. Or imagine you're in charge of your product's R&D initiatives and want to understand what new features could be incorporated into an existing product based on what people are searching for. What's popular and relevant might even inspire a new product line for your team. Terms that appear in these data sets can be an indicator of what you should be paying attention to. The data signals dataset provides the top 25 stories and top 25 rising queries from Google Trends. These are accompanied by a rolling 5-year window of historical data in 210 distinct locations across the United States. Additionally, we've recently introduced the ability to access this data set for areas covered internationally. That is, where the Trends service is globally available we address data covering approximately 50 additional countries worldwide. Our second key building block is Google Cloud Retail Search, a purpose-built industry solution that gives retailers the ability to provide Google quality search on their own digital properties. Retail Search is a fully managed search engine capability which helps customers find the products they're most likely to find relevant across your own or their own product inventory. It's a fully customizable solution that allows us to provide helpful search experiences, including autocomplete, personalized results, and tunable filtering, pagination, and ranking. Now, from a developer perspective, you simply provide or supply your own custom product catalog and some supporting configuration data. There's no need to pre-process the data, train or hyper-tune machine learning models, nor load balance or manually provision infrastructure to handle indexing, processing, or serving. We do it all for you automatically. At the end of the day, your team can then interact with the underlying search service through our defined APIs, SDKs, and web tooling experience. What gets presented as output are continuously refined search results triggered by search term queries. In many cases, we can simply end the integration process right there, but some domains and use cases may benefit from additional search result processing. This leads us to building block number 3, the Vertex AI Matching Engine service. This service provides tooling which allows us to further refine our previous search results by applying semantic similarity checks. More specifically, given an input query term, Matching Engine finds the most thematically or contextually similar item set from a general corpus of candidate documents or records or items. Note that the state-of-the-art paradigm for building semantic matching systems is generally built by computing vector representations of all candidate items. These vector representations are often called embeddings. Embeddings are computed by using various machine learning models, tools, and techniques. The models are trained to learn an embedding space where similar examples are close while dissimilar ones are far apart. The closer two items are in the embedding space, the more similar they are. Now, as a standalone service, Vertex AI Matching Engine provides a high-scale, low-latency, vector similarity matching capability which wraps this all as a managed service. Note that vector similarity matching is also known as approximate nearest neighbor capabilities. The matching engine is capable of finding these nearest neighbor items or records in milliseconds. It's highly performant. And it can perform this operation across billions of candidate vectors, all while allowing end application developers to consume fewer CPU cycles when serving out these results, especially as compared to self-hosting these capabilities using other library implementations. To better explain the concepts behind semantic or vector similarity matching, this illustration shows how this technique can be applied to the problem of finding books sourced from a database that are the best semantic match to an input query. To answer a query with this approach, the system must first map each database item to an embedding, then map the query to the embedding space. The system must then find among all database embeddings the ones closest to the query. This is the nearest neighbor or vector similarity search problem. The use of embeddings is not limited to words or text, however. With the use of machine learning models, aka or often deep learning models, one can generate semantic embeddings for multiple types of data, for example, photos, audio, movies, and user preferences. But for our example today, we'll focus on the specific application of vector similarity on refining retail search results by creating and processing embeddings using the textual metadata backing our product catalog records. So let's put this all together. Recall that we are presented with the opportunity to turn large-scale search signals into queries against our product catalog. and then refining those results to ensure we achieve maximum coverage and relevance. At the end of the pipeline, we can then use the focused result sets to build a featured content gallery or top shelf portion of our overall application experience. There are a number of key components and technology services that we'll leverage in building this solution architecture, and you can see some of them listed below. We'll actually put that in context on the following diagram. Again, from left to right, we consume regular search trend signal data via the data signals dataset. This dataset's published as a tabular stream contained within the Google Cloud SQL data warehouse service known as BigQuery. From there, we'll apply some optional enrichments to ensure we tune our search queries with relevant, amplifying context. This is especially useful for scenarios outside of core retail operations. We'll then query the retail search service and attempt to identify the most user-relevant items in our product catalog based on the inbound search term, the context around it, and potentially other rules or learned preferences. A second and final pass is made to then take these results and check for semantic similarity, allowing us to filter out low-scoring items based on thematic match against the original search trend signal. Our final optimized result set will then be passed back to our application interface where it can be presented to the end user. So let's walk this through with an example. Here in Los Angeles, as is common throughout the year, we see certain Google search terms come and go based on overall popularity. One such term that appears often are search terms related to football or soccer. Man United in particular, or Manchester United, an English Premier League team out of the UK, garners plenty of interest here in LA. So how can we take advantage of these bursts of signal data originating from fans or potential fans of Manchester United and turn these into actionable experiences? Whether it's promoting branded sports gear and swag, to highlighting and directing customers to live events and packaged ticket offers, to recommending media assets associated with football, soccer, Man United, and their graph of connected celebrities, events, and themes. This is where we'll focus our example. We'll identify the main ingredients to building a top-shelf widget for a fictitious video/over-the-top application, one which highlights video content in our catalog deemed most relevant to trending views, news, or viral search interests. That is, starting with item number 1, we'll need to respond to recent local community search trends related to the term, quote, Man United, unquote. Item number 2, we'll then convert these search term signals into directed queries against our custom product catalog, using the well-known Movie Lens dataset as our sample product inventory. Finally, item number 3, we'll take the candidate set of search results that qualify and further refine, rank, and optimize based on whether the products are deemed semantically or thematically related to the original search signal, therefore resulting in a crisper, focused result set that we can then place on our video app's top shelf. We'll step through the main service ingredients using the following flow, from signal to enrichment, then search, and finally refinement. Let's start with our source signal. Recall that we can retrieve the top search trends in our local community by tapping into the publicly available dataset hosted in Google Cloud's BigQuery system. For those familiar with SQL, this is a simple matter of pulling the table elements from the regularly updated table hosted as a BigQuery dataset. Note that we can accomplish this by establishing a connection to the BigQuery service through your existing Google Cloud Platform project account or via the free sandbox that's generally available to anyone with a Google account. The details of this are available at the links cited on these and the following pages. When querying this dataset, we use standard SQL syntax to extract key fields of interest from the designated top terms table as shown here. We can further qualify our search to pull back data refreshed in the last day, aggregated around the directed marketing area of Los Angeles, and sort our results by time and overall search popularity. I invite you to explore the published schema in the above links to craft your own custom query offline. For our mini example, here's a screenshot of the developer experience on the web console. We've slightly modified the SQL to extract the information pertinent to our example. That is, we highlight the key search trends that were popular in the Los Angeles marketing area, refreshed for the time period in question, June 13. We can then take these search results and programmatically extract these out as a part of a regularly scheduled data pipeline. For our example here, we'll simply use the built-in BigQuery web console feature of being able to export this to the next portion of our sample flow. For example, we can export these out to a new line delimited JSON file and store these on disk, or better yet, on Google Cloud Storage, aka GCS. Google Cloud Storage is a highly available object storage service well suited to big data, analytic, and data science workflows. Latest trending terms in hand, we can then proceed to the next stage of our workflow. Note that in the simplest of cases, we might be able to turn right around and search for products in our business catalog or product inventory which match our trends data. However, at the moment, search trends results do not yet include amplifying context, which can guide our discovery process and help us differentiate between general categories of interest. For example, a popular search term of quote-unquote The Rock may refer to either a well-known movie or perhaps a present-day celebrity, aka Dwayne The Rock Johnson. Overall, running our search terms through another step to predict the overall context may prove helpful. To achieve this, we can leverage any number of natural language processing capabilities available to us. Here we'll use Google Cloud's Natural Language API, available through a variety of interfaces including Console, Web Service, SDK, or in this case through the command line interface utility known as gcloud. We can pump our search term signals into this part of the pipeline to extract, for example, key characteristics such as ML-derived entity types and supporting metadata such as the estimated Google Knowledge Graph ID and the most relevant Wikipedia resources mapped to these search terms. Knowing the type of object we're dealing with, whether it's an organization, location, event, work of art, or other, can be helpful. Additionally, having access to an associated open source wiki reference helps us pull down additional descriptive text about the search signal. In this case, we could see that the terms Man United versus Liverpool, quote unquote, map to our intuition that they represent two distinct entities, in fact, two well-known sports teams part of the Premier League. We can use the predictive entity types, the Google Machine ID or MID, and the Wikipedia asset as additional hints that allow us to shape our remaining search operations. We'll use this data in particular when we work with the Vertex AI matching engine to generate embeddings from search term fragments and amplifying Wikipedia summary text. We'll revisit this shortly. Which brings us to search. Recall that retail search service requires that you supply a custom product catalog for indexing and subsequent discovery operations. The ingest protocol generally relies on a few core metadata elements, such as unique product identifier, descriptive title, and summary text about the product. Additional information can be added to the record, such as product imagery or cover art, business-specific tags, crawlable product web page links, and extensible attributes that are tailored to your domain. For our example, we'll extract movie data sourced from the Movie Lens and TMDB resources. We extract metadata for roughly 60,000 titles and format as new line JSON input records, compatible with the retail search schema. These are stored as batch import files and staged onto a common location such as GCS Google Cloud Storage. We'll then use the retail search import feature built into the Google Cloud Console. Here we specify a new product catalog import operation and provide a reference to the Google Cloud Storage location where we've staged our movie title product inventory. Once data has been ingested and successfully processed, our search index is ready for queries. We can use the available web service APIs and available SDK bindings to perform these search operations, but for our immediate example, we'll use the web console, which is suitable for rapid testing and evaluation. In fact, we'll go ahead and navigate to the Retail Search Evaluate page and then drill into the search operation. Using one of our inbound data signals, the search term Manchester United or Man United, we'll plug that right into our input search field. What comes back are a number of keyword-relevant results, largely matched and sorted based on matching tokens against product title, descriptions, tags, and custom attributes, all subject to filtering and boosting based on rules we previously configured ahead of time. Other factors, such as derived context and historical feedback from the user in question, may also play a role in generating these results. Overall, we get some pretty good results from our MovieLens and TMDB product inventory. There are occurrences of movie titles related to Manchester United, quote unquote, but we may also have some false positives just given our current setup. For example, movies referencing Iron Man, X-Men, and Manchester at Sea may all be interesting or enjoyable movie releases, but in the context of Man United, they may not completely map to the overall trending signal. A potentially significant user base in the LA region on the week of June 13 are very interested in all things related to the football club Manchester United, and so we should focus on that. It's at this point we can refine these results by applying the next level of processing, semantic match. Although aspects of this are organically provided by retail search, we show how using Vertex Matching Engine, we can extend this processing to other domains and maximize tuning and control over the last mile of refinement. But first, a little background on the concepts behind semantic matching based on vector similarity. As previously mentioned, we're interested in encoding data records into a form that embeds the intrinsic features and semantic relationship between those features into vector form, which ultimately allows us to compute nearness based on standard distance measures. For our sample use case, we construct text documents for each product contained in our catalog and then run them through available AI-based encoders known as transformers to derive the vector-based equivalent known as embeddings. Our protocol for generating these input text documents is to combine essential elements of the product record, such as movie synopsis, descriptive user-supplied tags, and comments. The output of this data preparation task are vector representations, one for each inbound catalog item, in our case about 60,000 records. Note our choice of open source or custom encoder will determine other output aspects such as the shape or number of dimensions of the output vector. Ultimately, we'll import these vector representations, aka embeddings, into our semantic matching engine. The Vertex AI matching engine will then handle all the infrastructure concerns with serving up and matching queries at scale. All we need to do is provide an inbound query document and call the service endpoint to find all relevant semantic matches. Note that the topic of choosing or training your own encoder model is currently beyond the scope of this talk. We invite you to learn more about these on the Vertex AI Matching Engine product pages. For our current sample, we'll use a representative model providing NLP text-to-text transformation known as T5. There are continuous innovations across the community, and you may find options that better suit your use case. Please feel free to explore these various model options. For example, that happen to be published and available on a continuous basis on open source forums and hubs such as TF Hub or Hugging Face Hub or others. Once the corpus of documents are encoded and uploaded, we're now ready to query the engine for semantic nearness based on input text fragments. For this portion of the walkthrough, we highlight key code snippets based on SDKs available for Python 3. First, we set up our imports and configure our Vertex AI Matching Engine web service endpoint. The endpoint's provided as a part of the service provisioning process described separately. We'll also use the popular open source package Sentence Transformers to help us with encoding our inbound query fragments. For this, we make sure to use the same encoder model we used offline to preprocess and compute embedding vectors for our overall movie catalog. That is, we make sure to use the T5 base model. Next, we take our input query and prepare it for semantic analysis. In this example, we use the same search term sourced from our trend signal, quote, Man United, unquote. For more robust processing down the road, we can include the optional entity enrichment processing described earlier, adding text fragments from, say, the authoritative Wikipedia summary for the Manchester United Football Club. We'll leave this as a future to-do and save the results for later comparison. In any event, the search term is then transformed by using the same T5 encoder model we used previously. With encoded query in hand, we can now pass this to the web service endpoint. We provide some additional config options, such as the maximum number of candidate neighbors or results to return. And just like with retail search, we receive a relevant set of results with low latency. The results are rank sorted in this case based on semantic goodness. We're provided with similar products by ID and the associated distance measure. A cosine distance metric is provided. The intuition behind this being that the record matches, which are very similar to the inbound trend signal, i.e. Man United, will have distance metrics closer to zero because the angle between the vector representations of these inputs versus corpus documents will be closer to zero. In our sample set, we find some interesting candidates not necessarily high on the list from our original retail search results, such as the film Iron Men, which may be syntactically distant from our original search, but thematically closer based on the matching engine's analysis. Overall, for our specific use case, we're likely to expand our reach by combining both retail search results with complementary results from the matching engine. We can prioritize results which rank highly in both assessments. For example, when triggered by a search for Man United related videos, our first pass reveals certain movie candidates, as we've seen previously. Based on a second pass with semantic matching in mind, we subsequently decide to drop those items which score poorly in terms of semantic closeness, and then optionally add in some additional bonus items which we believe may be relevant and may help diversify the overall recommendation list that appears in the top shelf. And in this specific test case, we find an interesting action title film from 2001 called Shaolin Soccer. No comments needed. So finally, at the end of this two-pass process, we gather the best of and generate our final community-driven video recommendation playlist. For our fictitious but growing video service app, we can see that these are generally intuitive movie product matches based on trending interest in professional league football scores, and overall is an example of where we can combine numerous unique signal data and search solutions to create meaningful user experiences. All right, so in summary, we've described a solution integration which combines three key capabilities to turn trending search signals into tailored product recommendations from a business-specific product catalog. That said, we recognize that there's an extremely large base of innovation in the recommendation space, And what we presented today represents just one possible technique that may be part of an overall strategy for providing relevant content to our customers. For example, we might combine today's solution topic with standard collaborative filtering techniques, which rely on feedback and ongoing interaction from users. Our technique described today could also be used to bootstrap this recommendation flow, especially when we're dealing with new users and/or challenged with cold start issues. More information on the components of today's solution overview are provided in the links below: data signals, retail search, and Vertex AI matching engine. And with that, I'd like to thank you for your time and attention today. And our collective team is always happy to assist as you explore new ways to turn trend signals into action.